In this video, we're going to deal with the refraction of light. Refraction is the change in direction of a wave that is passing from one medium to another caused by its change in speed. When light rays travel through transparent materials, if they reach a boundary between two different mediums, there is a change in direction because of the change in density. So it can be illustrated using light rays traveling from air into water or air into glass, any different medium. So if we look at this coin in the bottom of the cup, we'll wait until it gets to the beginning of the little animation. If we see the coin at the bottom of the cup, the light rays originate from the coin and bend or refract as they pass from the water into the person's eye. So there we see two rays of light traveling from the same point on the coin, and at the surface of the water where they travel into air, they bend. Those rays of light would travel into the eye, and what it would appear as if the rays were traveling straight and originating from a point a lot higher, shallower than the actual position of the coin. So the image appears closer to the surface and further in front than the object actually is. If we look at this glass, as water is poured into the glass, you can see that the arrow changes size and it actually changes direction due to refraction. And you could try this at home and prove it for yourself. So now we're going to use ray diagrams to show how refraction occurs. So we'll illustrate what happens to light rays as they travel through a parallel-sided glass block. The parallel-sided glass block is, as it is labeled, it's got two sides, each of its two sides, its faces are parallel to each other, just like that. So we have a ray of light incident on the surface of the parallel-sided glass block, and the ray of light must be incident at any angle other than 90 degrees. If it was incident at 90 degrees, it would pass through without bending. So there we have our incident ray. Once the incident ray has been drawn, then you'll draw a normal line at 90 degrees to the surface of the new substance, as shown here. The ray of light then changes speed and direction as it passes into the glass block. Because the glass block is more dense than the air, the ray of light is traveling from a less dense medium into a more dense medium. The light's going to slow down and bend towards the normal, so the angle of refraction is going to be less than the angle of incidence. And the refracted ray bends towards the normal. As the refracted ray reaches the boundary, the second boundary between the glass and the air, a normal line is drawn again because the light is then refracted again, this time away from the normal. There's the normal line, and when the ray of light travels from a more dense medium into a less dense medium, the light speeds up and bends away from the normal. If a ray of light is refracted through a parallel-sided glass block, at the first surface it's bent towards the normal, and at the second boundary between the mediums it's bent away from the normal. What will happen is the two rays of light, the incident and the emergent ray of light, the two rays of light that are in the air, will be parallel to each other. So if we remove the refracted ray and put in some parallel lines, you see there that the incident ray is parallel to the emergent ray. This is what occurs when light is refracted through a parallel-sided glass block. When light travels from a more dense medium into a less dense medium, it's bent away from the normal. This we've just learnt with the parallel-sided glass block. And the angle of refraction is always going to be greater than the angle of incidence because it's being bent away. So we show this in the diagram here, the incident ray put in the normal, and we see that the ray is being bent away from that normal, so the angle of refraction is greater. As we increase the angle of incidence, the angle of refraction is going to increase. So we see here now we've increased the angle of incidence, the angle of refraction has increased. If we keep doing this, we reach a point where the angle of refraction becomes 90. When our angle of incidence has increased so much that the angle of refraction is 90 degrees, then we call the angle of incidence the critical angle. And beyond that point, refraction no longer occurs, which we're going to see in the next diagram. So light is refracted along the boundary between the mediums when there is a critical incident angle. If we increase the angle of incidence beyond the critical angle, refraction no longer occurs and the ray of light is reflected within the more dense medium. This is called total internal reflection. The ray of light is reflected back into the more dense medium. So the law of reflection is then obeyed and the angle of incidence is equal to the angle of reflection.